Hey guys, Greaves here. Going to take a look at review 13. Okay, so let's take a look first. Review 13, what do we have? Well, setup of I got a block and a spring on a frictionless table. Pull back some distance x, let to go, and it zips off. Okay, so 13 looks, it's gonna, based on this situation, right? So let's take a look at the first thing. Calculate the time elapsed for the block, right? To hit the ground. Okay, so 13.1a. So 13.1a. How long does this take and hit the ground? Okay, so what do I got? Well, it just looks like I have to do a simple linear motion. Delta y is going to be what? v0t plus 1/2 a t squared. So delta y, how high are we? 0.8. Obviously that's 0, right? 1/2, 10 t squared. Doing a little bit of math, 0.4 seconds. So it takes 0.4 seconds to hit the ground. All right, next was the next one say. All right, calculate the speed of the block as it leaves the table. And just to give you a quick heads up, when I first do this, I said, this one's gonna be easy. I got a spring compressed some distance, u equals k, and then I said, well, wait a second, I don't have k. Sorry, I don't have x, right? So it looks like I gotta approach this in a different way. All right, upon looking at it again, right, I know, right, how long it's in the air, and I know how long, right, I've been traveling horizontally. So it looks like I can use the same exact relationship, right? So 1b, delta x is equal to what? v0t plus 1/2 a t squared. How far did it travel? 1.2. Right? Obviously, since it's traveling horizontally, there's no acceleration in the vertical, in the horizontal. So I know I just found out that, well, I'm sorry, I want that, and it was 0.4 seconds. So doing a little bit of math here, 1.2 divided by 0.4, right, I get V0, 3 meters per second. All right, not terrible. C, all right, now C says, calculate the distance the spring was compressed. All right, now we do u is equal to what, k? So 1/2 k x squared, 1/2 mv squared. Slash and burn those halves, 650 x squared, 4, and we just found out that that was going 3 squared, that bad boy. Right, so doing a little bit of math, I got x is equal to what? 0.23 meters. All right, next one, right? Okay, so now, same exact scenario, but things are a little bit different, right? I'm going to stick a same exact block right here. Same identical block. Let this guy shoot off just like it did before, but it's going to crash, right, and stick to B. Then it's going to sail off. Now it wants to find out how far did it go. Well, we do know some information. We know that it's been in the air for 0.4 seconds, right? If it's been in the air for 0.4 seconds, if I find out how fast I'm going here, then I can find out the distance. So what am I going to use to find out how fast things are going here? Well, in this particular case, right, so for D, I'm going to have to do a little bit of momentum first, right? So what does momentum say? P before equals P after. It's just saying momentum is conserved. How many objects did I have before? One mass traveling one velocity, crashes and sticks to the same exact mass, it's going to have a new velocity, right? So what do I have? 4 kilograms going 3, crashes and sticks, right? So 4 plus 4, that's 8v, right? So 12 divided by 8, v is equal to 1.5 meters per second. It's not really what it was asking, right? It's asking how far from the ledge is it going to go, right? So delta x, v0t, plus 1/2 a t squared, that goes to 0. So 1.5 times 0.4, right? And we got 0.6 meters. Cool. All right, next one. What does the next one say? All right, now, next one. What do we got here? All right, the next one, I like this problem, and guess what? So do the AP. They love these types of problems. So let's consider the system consisting of the spring, block, and table. How does the total energy E2 after the collision? How does the energy after the collision compare to the total energy before the collision? All right, so let's think about something, right? we said that these two guys crash and stick. So a crash and stick problem is inelastic. Inelastic, some of the energy must be dissipated, right, to conserve momentum, right? So let's take a look. What do I have? It's going to be E1. The answer is E1 is going to be bigger than E2. Let's take a look. So what am I saying is E1 before, right? So I have one object, right? This crashes and sticks to 2. Now, the answer is E1 bigger than E2. Why? I'm going to tell you why. Inelastic, energy must be dissipated to conserve momentum. But if you don't believe that, right, let's take a look. Let's do some math, right? So let's take a look. I just have this 4 kilogram object, right? And what did we say it was going? 3 meters per second. 1/2 mv squared. How much energy is here? 1/2, 4, 3 squared, right? 9 times 2 is 18. So in the beginning, E1 is equal to 18 joules, that is. What happens after? 8, it's going 1.5. 1/2 mv squared. 1/2, 8, 1.5 squared. Believe it or not, this E2 is equal to 9. So the answer is, like I said, E1 is greater than E2. Explanation, inelastic, energy must be dissipated to conserve momentum. Right? Okay, so that is 13A. All right, let's take a look at 13B. 13B has ourselves a pendulum, right? Swinging back and forth. Okay? Part 1, part 2. Okay, I should say at point 1 and at point 2. So let me just get my notes here for a second. Here we go. So what is it saying? On the dot, and I'm just, by the way, I'm just going to, you have a grid there. I'm just going to draw it here. On the dot at point 2, the free body diagram. Draw the free body diagram for point 2. Okay, now, what's happening here? Believe it or not, it's swinging back and forth, but it is traveling in a circle. So it must have some sort of what? Centripetal acceleration, right? So something that's traveling centripetally, right? There must be, right? Must be a force, a net force allowing it to do it. So this is going to be mg. Now on you have a grid, right? Boxes, right? So that's mg. No matter what, this guy here, the tension has to be. So the tension here has to be bigger than mg, right? Because since the only way that it can travel centripetally is if there's a net force to do it, right? And that's really what that question is just asking, right? So the tension has to be bigger, right? Okay, so that's that guy right there. What is the next one saying? Right, so that's that. My notes, flipping around for a second, guys. All right. Okay, so that's that. Next one. Calculate the maximum kinetic energy. All right, so kinetic energy. So how do I get the maximum kinetic energy? So kinetic energy is going to be equal to 1/2 mv squared, right? 1/2 mv squared, right? But I can't find the velocity, right? But guess what? As this guy kind of swings what? Back and forth, U here is going to be equal to K. So guess what I can do? I can kind of calculate the potential energy, set that equal to the kinetic energy. So really my kinetic energy is going to be equal to what? mgh. All right, I know that this is 0.2 kilograms. I know that this is 10. All right, here comes the problem. How do I get the height here? All right, so how do I get the height? Okay, to get the height, no matter what, I'm going to need to find this length, right? All right, so how do I find the length of a pendulum? Well, if you look at your reference table and remember, the period of a pendulum is equal to 2 pi L over G. Sorry, G, not Q. G, right? All right, so that leads me to, all right, I want L, I know G. What's the period? Well, we're going to have to go to my graph, right? What is my graph telling me? Well, if I start here, horizontal position, it tells me that it completes 1 cycle in 2 seconds, which is the period, right? So 2 seconds, 2 pi radical L over 10. Now, I did this already, right? I'm not going to go through the math with you, right? So when we do this, I get a length of 1 meter. All right, so I have a length of 1 meter, but I still need this height right here. So let's expand this just a tad, okay? So there is my pendulum, where this being L, okay? Right? And this is also L, right? This is going to be what then, right? So this is L, right? This is, right? And this here, what's this? So if this is 15, what is this guy right here, right? This is going to be L what? Adjacent cosine theta, right? This side. So what does that leave this side being, right? So here's L cosine theta, and this is L. So this here has to be what? L minus L cosine theta. So that's my delta H. So what do I have? 1 minus 1 cosine 15. And like I said, I did this already, and you're going to get something like 0.03 meters, right? So put the 0.03 meters in there, and you're going to get something like 0.68 joules. So that's that guy right there. It's a little involved, a little tough, I must say, right? So that's that guy. What else did we want here? And this guy. Right? All right, explain how the motion of the sphere changes, if at all. Right? So the sphere is raised to a nu, right? So I'm taking this. So here we have it here, right? There's my pendulum right there, okay? Original. I'm going to take it, I'm going to put it there, right? And it's going to swing back and forth, back and forth. Well, what's going to happen, right? What does it really say? It says, explain how the motion of the sphere changes, if at all, based on appropriate evidence. Well, I'm going to say it doesn't change, right? Why doesn't the motion of this pendulum change? Well, let's take a look at the period of a pendulum. There's the period of a pendulum. Does anyone see in there the angle theta? The answer is no, I don't. So this motion does not change because the period of the pendulum is dependent upon the length only. All right, so there's 13. See you guys soon.